All right, so hello everyone. Thank you for joining us for today's EEA Education Series SIG. Today we will discuss demystifying Ethereum building blocks with consensus, encryption, and ZK proofs. Everyone is in listen-only mode. However, you are encouraged to ask questions by using the question box on your control panel. Today's call is being recorded and will be available to all attendees soon after today's presentation. The Enterprise Ethereum Alliance is a member-driven standards organization whose charter is to develop open blockchain specifications that drive harmonization and interoperability for businesses and consumers worldwide. We welcome any and everyone to join and become a part of our global community. At this time, we are pleased to introduce Ken Fromm, the SIG's director.
Hi, welcome everybody. Glad you could join us. Pleased to present to you. It talks about zero knowledge proofs as well as consensus algorithms with emphasis on how they fit into the overall blockchain environment and tool set. So without further ado, I'd like to introduce Jacob Eberhardt. He will discuss zero knowledge proofs. Jacob.
Hello everyone. I hope you can hear me well. I'm also watching the chat and I'm trying to also watch the question section, so feel free to get in touch whenever you want or can during the talk as well. So I'm here today to talk about zero knowledge proofs in particular in Ethereum, and I'm trying to cover the foundation tools and applications. So I'm Jacob. I work as a researcher with a focus on blockchain technologies at Technical University Berlin. And I also started Socrates, which we'll cover in a bit more detail later, which is now further developed in an Ethereum Foundation team. So yeah, I have both shoes on today, you could say, coming from practice and working within the Ethereum Foundation to provide good tooling for zero knowledge proofs, and also from academia, which takes care of the foundation in a bit more detail. So today I'm trying to answer three basic questions. I want you to take away three things. So first of all, what are zero knowledge proofs? And I'm not talking about the nitty-gritty math details. There's plenty of talks on that, but more about an intuition, what it is, what they're for. Then I want to talk about why they're relevant for Ethereum and relevant for blockchains overall. And then I want to talk about how we can use zero knowledge proofs in Ethereum today, what applications are, and how people can actually build on zero knowledge proofs. So I want to start with a little introductory example. I think you're probably all familiar with the game Where is Waldo? And here it's just about providing an intuition what a zero knowledge proof is. I hope we have people using the chat at the moment. So I'll just ask a question, wait for like 15-20 seconds. If you have any clues or ideas, please post them in the chat. If not, I'll just give you the solution afterwards, and it will still be a good learning experience, I hope. So the first challenge is we have two people. It's Alice and Bob. They're probably kids. And Alice found Waldo somewhere in this picture. And now she wants to prove to Bob that she found Waldo, but she does not want to reveal that where Waldo is, because she'd spoil the game for Bob afterwards. But she wants bragging rights, let's say. Are there any ideas that you want to post in chat how we could design a real-world zero knowledge proof to show to Bob that Alice found Waldo in this picture? Okay, no activity yet, no ideas yet, so I'll just jump to the solution. So the idea is that we take a very large sheet of paper and then we cut out Waldo and we make this paper much, much bigger than the initial Where is Waldo puzzle. And then we just put it on top. So Bob will be able to see, okay, Waldo is in the picture, but he'll not be able to deduct more information about where in this original picture it is. So that's like the first real world zero knowledge proof we have here, because we can now prove to Bob as Alice that we know a solution to a puzzle or a problem, but without revealing anything but the fact that we know a solution. Bob learns nothing about the position. Second little introductory puzzle is the my card is red puzzle. So let's say we have a deck of cards and we want to prove to someone else, let's say we have Alice and Bob again. Alice wants to prove to Bob that she has a red card. So we have the deck. She draws a card from the deck at random. She figures out it's red, but she doesn't want to reveal which card it is exactly. She only wants to reveal the fact that the card is red. Are there any proposals on how that could be done? Okay, nobody at this point. So the idea here is to basically reveal all the black cards, because then Bob would be able to check that the set of black cards is complete, so he knows Alice must have a red card, but he has no clue which red card Alice actually has. So again, we have a zero knowledge proof in the sense that we have a statement which would be my card is red, and we later call that verifier. The person who checks it learns nothing but the fact that the statement is true, but he doesn't learn which exact card it was. And here's the probably most famous example, but I think it's nice because it also covers interactiveness as a property. It's called Alibaba's cave. And here we have Bob and Alice again. Bob standing outside of the cave, whereas Alice is here at the entrance of the cave. And Alice knows the secret how to open the door in the back of the cave. So there's that secret door, and you need to know a secret keyword, and then the door will magically open. That's the nature of Alibaba's cave, you could say, and then you can walk past. So Alice basically claims that she can do a round trip through the cave, and she'll be able to open the door. And she wants to prove that to Bob, but because it's like a superpower to be able to open the door, she doesn't want Bob to learn the magic keyword. So she cannot go into the cave together with Bob, because Bob would hear her saying the keyword, and then it will no longer be her personal secret. So the question is, how can we design a protocol here that Bob is convinced of the fact that Alice knows the secret keyword, but does not learn the keyword in the process? Any ideas in chat? Oh, someone's posting in question sections. Very good. Okay, so it goes in the right direction, I think. The idea is that they agree that Alice walks into the cave and opens the door while Bob stays outside. So she walks in, just chooses one random path, opens the door, and waits. And then Bob goes in after her and tells her which side he wants her to come out from, right? And then, since Alice opened that door, she can come out at either side. So whatever Bob would say, Alice would always be able to exit on the correct side. If Alice would not know that secret keyword, she could come out on the correct side in roughly 50% of the cases if Bob chooses at random. Oh, I just got the info that you guys can only use the question tags and not the chat. So yeah, just posting questions. I'll try to watch the question section as well. Yeah, so since Alice is able to open the door, she'll always be able to come out on the correct side. And since Bob, if they do that experiment only once, could just think, oh, Alice got lucky and went in on the right side, but she didn't actually open the door, they can repeat that experiment over and over again. And over time, Bob will be more and more convinced that this is actually working and Alice actually knows the secret. So that was the 3 examples of zero knowledge proofs in the real world, which I think can be useful to provide an intuition about what these protocols are all about and what properties they also have. Now let's come to a bit more formal or a bit more, computer sciencey definition. So zero knowledge protocol is a protocol that allows a prover, in our case that was usually Bob, to convince a verifier of the validity of a statement for a given input without revealing any information but the fact that the statement is valid. We had statements like, my card is red, or I know where Waldo is, or I can open the secret cave door. and then we manage to find protocols so that in the end, the verifier is convinced by the prover. Here's another interesting problem, just to define terminology a bit more. The statement here is, I do not know anything about the integer solutions of this equation down here. This is the statement. So x cubed plus y cubed plus z cubed equals 3. And that's like a challenge that was posed in 1953. And the author identified 2 known solutions and basically conjectured that there are probably other solutions, but it must be very hard to find those other solutions. And only in 2019, a 3rd solution was found. And this is what we typically refer to as a statement, basically just some conditional, a statement that can be verified when you receive a solution. And typically in the context of zero-knowledge proofs, these solutions, or they're called the witness because they actually witness that the statement is true. You can check that this equation works with these witness values down here. So that's a bit of terminology that can come in handy. The question now is, with such protocols in computer science, what can we prove? And there's a fundamental result by Goldreich, Oded, and Silvio Micali and Witterson, and that states basically that any NP statement has a zero-knowledge proof. That's a very computer sciencey definition of things, so not everybody may be familiar with it, but it basically says that there are zero-knowledge proofs for statements that are easy to check for computers. So that circuit satisfiability, graph coloring, the knapsack problem, all these things you learn in a basic complexity theory course at universities. So what we know now is basically for a large class of relevant problems, we have zero-knowledge proofs. So we can prove that statements are true without revealing any further information. The question now becomes, after we know that there exist these proofs, how can we ensure that these proofs are efficient, in the sense that proofs are fast to create, they're small, they're cheap to verify, and they are overall practical, you could say. You can work with them and it's not just a theoretical system someone thought up. And the second question is, we have that computer sciencey definition of things up here, and how do we express meaningful things as such NP statements, or in general as statements that we can then prove with zero-knowledge proofs? And I'm going to spoil a little bit here, later parts of the talk. We can ensure efficiency just by using modern protocols, state-of-the-art protocols, for example, CK-SNARKs. We'll go into a bit more detail later in the talk. And we can also express meaningful things in provable abstractions by using high-level programming languages such as Socrates, which basically means we do not have to understand the mathematical foundations and how these statements can be defined from a mathematical perspective, but we can write programs in a high-level language, and then we can execute them, and then we can prove that the execution happened correctly. But now I talked a lot about zero-knowledge proofs and all that, but the question is, how is this even relevant for Ethereum and the Web3? Sure, it's kind of cool tech, but we haven't talked about how this works out. As I see, the second speaker is not in the meeting yet, so I'm not sure he's going to be here unless we've heard anything from him in the background. So I'll probably take a little bit more time and talk about the relevance for Ethereum and how Ethereum basically works and why this is relevant in a bit more detail. I hope that's okay. So zero-knowledge proofs and the blockchain, why are they important? To understand why they're important, let's first look at how transactions are processed in Ethereum, and we'll simplify the description just a little bit so we focus on the important parts here. So for now, we leave zero-knowledge proofs behind us and just look at transaction processing in Ethereum from a high-level perspective to understand how they relate. What usually happens when someone wants to send a transaction, a node collects a transaction on the block. So a user submits a transaction to a node in a network, and the node collects several transactions in a block, and the block is basically simply a means of batching things together so that agreeing on the order of transactions in the network can happen on a per block basis and does not have to happen on a per transaction basis. And then we use a consensus algorithm that can be proof of work, proof of stake, other things, delegated proof of stake, doesn't really matter at that point. We use a consensus algorithm to select a node that is allowed to write a block. And then that node sends that block to other nodes in the network. And these other nodes independently validate the block by validating all the transactions that are contained in the block. Please let me know if you have any questions at that point. This will be very basic and boring for some, but it's important to understand how transactions are processed in the Ethereum blockchain because it defines key properties. It ensures that we have trustless processing of transactions. We do not need to trust a single entity for transaction processing to happen correctly in the network, simply because every node independently validates the correctness of all transactions. But at the same time, that means we process transactions redundantly. So the consequences of this mode of operation that we desperately need for the desirable properties of Ethereum to emerge, such as censorship resistance, and that we do not need to trust any central entity with the correctness of the processing, it has consequences, right? And that means since every block is validated by every node, adding more nodes to the network does not speed up transaction processing. This is very different from regular distributed systems design, where we usually add nodes just to scale the system. And a second consequence is that every node requires all transaction input data for validation. That means we cannot have any form of privacy or confidentiality in transaction processing, because if we keep data away from nodes that are supposed to validate transactions, they couldn't. So everything that is processed on the blockchain in Ethereum has to be public to the network. And now let's look at how that relates to zero knowledge proofs and things we can do. So before we discussed that with zero knowledge proof, we can prove statements, and these statements can be fact-checked essentially, but without revealing any further details about the solution to the problem or any other information but the fact that the statement is true really. And we can use that in the context of blockchains to do some different kind of processing, and I call that off-chain processing or off-chain computations. The idea here is that instead of, like we see on the left side here, the regular transaction processing and blockchains where you send a transaction to the network and it's re-executed by every node essentially. Instead of that, we send the transaction or some computational task to an off-chain node, some computational resources that are not part of the blockchain network, and then these nodes execute a program, right? And then they create a proof using zero knowledge proof technology that they executed that program correctly, and then that proof is sent to the blockchain. And then the blockchain nodes only verify that proof and do not re-execute the computation in the first place. So the idea is take a computation or some computational statement, process it outside of the blockchain, and using these cool zero knowledge proofs we have, prove that you did that correctly to the blockchain, and make sure the blockchain only verifies the fact and does not derive the fact on its own. So that reduces the role of blockchain nodes from a processor, from basically a server that processes transactions on a user's behalf, to a verifier. It basically only verifies that computations that happened elsewhere happened correctly. And now let's look at the nature of these proofs and resulting properties. So if we have some kind of proving scheme that ensures that the verification of a computation or a transaction is cheaper than the computation on the blockchain itself, then we have an improved scalability, because what we need to do on-chain is less expensive. In Ethereum, that would mean it uses less gas, there's less computational complexity. And a second consequence is that if we use zero knowledge proofs here, we can use information in that off-chain processing on that yellow node here on the right side that does not have to be revealed to the blockchain network, and the blockchain network will still be able to verify the correctness of the off-chain computation. And that's the power of zero knowledge proofs here, and that's why they are interesting in the context of blockchains. So the first statement here, that we can improve scalability by doing off-chain computations that we can verify with regards to correctness, that is basically a property we get from any type of proof, computational proof. And the second property here is one that's specific to zero knowledge proofs. If we use zero knowledge proofs to do these off-chain computations or to prove the correctness of these off-chain computations, then we can be sure that we have these privacy or confidentiality benefits as well, because we can work on private data that does not become part of the blockchain history. So that's kind of the idea how zero knowledge proofs relate to blockchain. There is lots of layer 2 stuff and other applications, and I'll go into that, into more specific applications of zero knowledge proofs and zk-SNARKs in particular in the end of this presentation. I have a bit more time now, as it seems, so I'm going a bit slower and talking a bit more about these things. This is the basic idea, right? This is why zero knowledge proofs and blockchains are so powerful, because we can offload computational steps from the blockchain. Okay, I already told you earlier that we need to be sure that the zero knowledge proofs we use to prove some computational statements that we consider relevant are efficient. We haven't discussed how we define such statements yet, and we'll do that afterwards, but for now we'll take a quick deep dive into one of these efficient zero knowledge proof schemes, just so you understand what the properties are, what the numbers are, and yeah, which limitations they also have. And then we'll discuss how we formulate useful statements that we can then prove using such schemes like zk-SNARKs in more detail afterwards. So zk-SNARKs, I'm sure you've heard that in the context of Ethereum if you've been around for a while. It stands for zero knowledge succinct non-interactive arguments of knowledge, and it's basically just a very efficient cryptographic zero knowledge protocol. So the proofs it creates, they're very short, they're very small, and they're non-interactive. So unlike in the example of Alibaba's cave, where the verifier and the prover would have to do multiple rounds, only one message, only one proof can convince a verifier of a fact that we prove with a zk-SNARK. And that proof is very small. It's smaller than 1 kilobyte. I think currently the best scheme has 127 bytes. And that is a data size that's good in the context of blockchains, because that's an amount of data we can actually send to the Ethereum main chain without completely running out of gas right away. It's a zero knowledge scheme. And what's also important, but now more for the scalability aspect than for the privacy aspect, is that the verification cost is low. So the on-chain verifier has little work to do. And the computational complexity of the verification is independent of the complexity of the statement that we prove. So we may have a very, very complex statement that we prove, and no matter how complex that statement is, the on-chain verification cost is always the same. And there you can see that scalability aspect really kicking in. What you can prove with zk-SNARKs, when you look at the papers and the mathematical foundations, is you can prove the satisfiability of arithmetic circuits or rank 1 constraint systems. And as you can already see, unless you're like an expert and you really want to dive deep, that's not really a useful way of specifying statements. So we'll come back to that later, but for now we'll just have to accept that this is how, our statements have to be specified. How CK-SNARKs work, we'll look at an example here on a high level. Let's say we have a circuit or rank 1 constraint system, so one of these provable abstractions, and what this shows is that we have a statement that says a value set equals or is defined as x times y. So we basically say we have a variable set and it's the result of multiplying two numbers x and y, and that can be modeled as such an arithmetic circuit down here, but we don't really need to care about that too much for now. Let's look at the steps that are involved with proving that set actually equals x times y. First, in the context of CK-SNARKs, we need to do a setup, and this setup is trusted. So if this setup is corrupt, then fake proofs can be generated. I'll come back to that in a minute. This setup step that has to be done once per program. So we can execute this program, you could say, where we compute set from x times y any number of times. We need to do the setup exactly once. And then as the prover executes their programs for given x and y and finds a solution set, the CK-SNARK scheme allows the prover to create a proof that shows that it actually found three variables, x, y, z, that fulfill the equation on the left, but only reveal the result set to the verifier together with the proof. And the prover can then check that the verifier can then check that the prover actually knows values x, y, z that fulfill the initial condition we have on the left, but it does not learn the values x and y in the process. In this talk, I'll not be able to go into the detail of how this works and what kind of cryptography is used. That's way too low level. So this is maybe a bit surprising that that actually works. But for now, we'll just buy that these cryptographic schemes are correct and working. So in summary, we have three steps. First, we do that setup step for a given statement or program, and we get these prover and verifier keys. Then using a prover key and inputs to a statement, we can then generate proof that shows that this statement is actually satisfied for the given inputs, but these inputs do not have to be revealed in the process. And then using only the proof and the verifier key, a verifier can verify a proof and find out whether it's true or false. The fine print is here. I mentioned this already, that this setup step create so-called toxic waste. That is information that can be used to forge proofs, and that information has to be forgotten. So this is either in enterprise context sometimes done as by a trusted third party, but this is not what we usually want in the context of blockchains. Instead, we can also use a multi-party computation, so a distributed setup procedure that will be secure as long as one of the participants is honest. And if you participate yourself in such a ceremony and you know that you behaved honestly, then you can be sure that this is not an issue for your application. Zcash, for example, when they did their first setup, they really paid a lot of attention to that, and someone was on a plane performing the setup there. But now with these new protocols, we can also have large-scale distributed setups where arbitrary people participate from all over the world, but it really depends on your application, what you want to do here. There are other efficient and practical schemes for zero-knowledge proofs for computational statements. There is CK-SNARKs that you oftentimes hear. Starkware heavily relies on that for layer 2 stuff. There's bullet proofs that are used in the context of confidential transactions in Bitcoin. They all have different properties. What's so nice about CK-SNARKs and why I cover that in more detail here is that the on-chain verification complexity is constant. So whatever your off-chain statement or computation is, the verification is always cheap, and they are by far the smallest proofs. So you can easily send them to Ethereum smart contracts and they can be verified without blowing gas costs out of proportion. And for the other schemes with stocks, it's usually more useful with batching, where you have several transactions that are batched together with only one proof, and then that warrants taking these or paying these higher costs for the on-chain verification. I hope that was not too much of a deep dive for this session. Feel free to ask any questions. That was basically just an outlook on how these schemes look in practice, what people mean when they talk about CK stocks, and whatever. Now I want to focus on how we can actually express statements that we want to prove with CK snarks without being domain experts, without knowing how to define these rank 1 constraint systems or arithmetic circuits that you've seen before. And this is actually a project I started and that is now developed further in an Ethereum Foundation team, and I'm also still working on it in that team and at the university, so we're still trying to improve it and advance it. It's called Socrates, and it's basically a language and a toolbox for zero-knowledge verifiable off-chain computations. So I pitched that idea of verifiable off-chain computations earlier when I tried to explain why zero-knowledge proofs are so powerful in the context of Ethereum. And this is exactly what this toolbox is built for. The idea is that you don't need to be an expert on these low-level abstractions or proving schemes. The idea is you simply write a program in a high-level domain-specific language that looks a bit like Python, and then you can run that program, and then you can generate CK snarks that prove that your program execution happened correctly. And then you can also use the tool to generate a Solidity smart contract, deploy it to the Ethereum blockchain, and that verifier that lives on the blockchain can then receive proofs that you created using that tool and verify it on the blockchain. So basically that's an all-in-one system that allows you to do CK snark-based off-chain computations. And since it uses a zero-knowledge scheme, it allows you to write programs that work on information that is not revealed to the blockchain network. So the abstractions we work with is that we have that high-level program code. That's what a developer writes. In the case of Socrates, it looks like Python a bit. And then this is translated into rank 1 constraint systems, then a lower level representation that we didn't cover in detail, is also not that important here. And then this abstraction is proven using a CK snark verifiable computation scheme. And there are different schemes that have slightly different properties that all qualify as CK snark. So that can be PJHR13 or Croth16 or GM17. I don't think we need to go into details here. The tool really abstracts this away from you completely. You don't really need to think about that much. So tools that support this, Socrates basically takes care of translating program code into provable abstractions. And then we can use established cryptographic libraries for zero-knowledge proofs like LibSnark or Bellman or Sexy to actually create these proofs that we require. The Socrates language, you can see a little example here on the right side, is a relatively easy to use imperative language, and you can define inputs to programs as private, and then they never leave your off-chain computation node, and it's designed to hide away the complexity that is usually involved with specifying CK snark computations. It's not only about defining these rank 1 constraint systems or arithmetic circuits, but making them efficient is a whole other deal that uses external witness derivation and non-determinism. Long story short, this tool abstracts that away. You don't need to take care of it really. And the language is designed in a way that it can be translated into efficiently provable lower level abstractions. So we can also make sure that the programs you specify in it can be proven efficiently, that everything is fast. If you want to try it out, you can try it out in Remix. just go to remix.ethereum.org. There's a Socrates plugin you can play around with, or you can just install it locally, and documentation is also linked here. Now let's briefly, before I come to a conclusion, talk about more specific applications of the ideas I introduced in this talk in the context of Ethereum. I'd usually already be way over time, and I would have gone quicker, so I haven't got a lot of in-depth slides, so I'll just comment on these briefly here. So Socrates, and with that CK-SNARK-based off-chain computations, have been used, for example, in the context of the EY Nightfall project, which is which implements anonymous transactions or transfers for tokens on Ethereum. That means ERC20 tokens, but also NFTs can be sent without revealing sender and receiver or value of the transactions with that project. And that project uses ideas that are also used in Zcash with CK-SNARKs to realize that idea. I think in the next education series call, there'll be more about layer 2 solutions, so I'm not talking about that too much here. But one example that uses CK-SNARKs and is considered a layer 2 solution are rollups, where you basically have the idea that you have an off-chain node, as I explained earlier, and that collects a set of transactions and basically executes these transactions, and to the blockchain it only posts a proof that shows that this transaction processing happened correctly and some metadata you need for that. Long story short, again, the idea is that we process a large set of transactions off the blockchain, and then the blockchain only verifies that everything happened correctly, but does not do the processing itself. Using a suitable verifiable computation scheme or proving scheme, we can be sure that this is more efficient than doing it on the blockchain in the first place. And oftentimes, depending on the data availability choices, we get privacy kind of for free in that setting, or at least we hide the information from the larger world defined as the blockchain network, and only that off-chain node sees all the transaction data. We've written a paper, it's called CK Relay, me and a co-author, and that uses CK-SNARK for blockchain interoperability. Maybe you know BTC Relay, which is a project by Consensus, and what it implements is a blockchain relay from Bitcoin to Ethereum. So it's basically an Ethereum smart contract and some other components that receive Bitcoin blocks and validate those Bitcoin blocks. And then Ethereum smart contracts can use that other smart contract that validated Bitcoin blocks to react on transactions that happened in the Bitcoin network. So it's essentially bridging Bitcoin to Ethereum, so we can specify smart contract logic that reacts to events that happened on Bitcoin. It's a bit more complex than that, but that's like the simplified summary. And the problem with that project is that it became very expensive to publish every Bitcoin block, which is created every 10 minutes on average, to the Ethereum blockchain, because the validation of a Bitcoin block on the Ethereum blockchain is quite costly, costs a lot of gas, and the data sent around is also quite big. So therefore, we propose CK Relay, which essentially batches a set of Bitcoin blocks together in a CK-SNARK proof that shows that these Bitcoin blocks were valid, and then the Ethereum on-chain relay component only needs to verify that proof instead of verifying all the Bitcoin blocks on their own. Because the BTC relay has been stalled for like 2 years now, I think, because it was just too expensive to run and nobody was willing to pay the gas fee. And with CK Relay and extensive badging of blocks, we can speed that up by a lot. So maybe you just Google the paper or send me an email if you're interested in that. And then there's also the baseline protocol. It's been discussed a lot in the EAA, I think, and it's also based on zero knowledge proof to implement business processes on the Ethereum mainnet without leaking any sensitive information from the businesses that are participating in these processes. So key takeaways of my presentation, which will come to a conclusion now. I hope I've answered the question of what zero knowledge proofs are as protocols. And we've seen some intuitive examples, but also a state-of-the-art scheme that is actually used on Ethereum today. I hope I was able to explain why they are relevant in the context of Ethereum, basically to allow decentralized applications to scale and to have better privacy and confidentiality properties than they would have had without CK-SNARKs or zero knowledge proofs in the case of full on-chain processing. And I showed that Socrates can be used by regular developers today and also has been used in practice to leverage that technology. With that, I'll end, and I'm happy to answer questions in case there are any. You can find me on Twitter. You can send me an email in case you want to know more about that. And yeah, thanks everybody for listening.
Thank you, Jacob, for joining us today. Please feel free to place your social media handles in the chat so all attendees can follow your work. If you're interested in all the leading blockchain work going on with EEA, please feel free to reach out to our membership director, Jack Lee, or send an email to membership@entethalliance.org. Again, that's membership@entethalliance.org. Thank you. This concludes today's EEA Education Series webinar.